Okay, so we're going to carry on talking about interpolation here. We're going to use another technique today that involves divided differences. That has some advantages over the other techniques we've looked at so far. So let's just try to remember where we were. Last time we talked about the Lagrange polynomial basis. This had some advantages, right? They're quite easy to use. It was easy to figure out what our coefficient should be here. We have exact formulas. It makes it very easy to prove things. But the downside is there's quite a lot of work involved in computing these things. You know, if we want to, say, not decide ahead of time what degree polynomial we should use, that means we might try to compute P1 and say that's not good enough. Well, now I have to start from scratch to construct P2, and if that's not good enough, I have to start from scratch again. So you have to really compute all of these polynomials up until the one you really want. There's no obvious way to reuse the work we've done already. So the idea is, well, if we've done a lot of the work, we should reuse it. In other words, if we've already constructed a polynomial Pn, an nth degree polynomial, it interpolates a lot of our data. Why should we throw out that work? We should try to keep that work and just make a correction to it somehow that uses everything we've already done and just does something very simple to add in information about one more data point that we want to add. Okay, so in other words, we say that we've already constructed this nth degree polynomial. It interpolates a lot of our data already, and we don't want to throw out any of that work. So if we want to, say, move up to an n plus first degree polynomial, we should keep that and then add on a new term, which has to be n plus first degree if we're going to get n plus 1 at the end. But this new term should be very, very simple, and it just should in some simple way add the information about the one new data point that we want to throw into the mix. Okay, so let's just think about what would have to happen if we could come up with a representation like this. Well, what would we need? Again, most of our data points are already being interpolated correctly using Pn here. Whatever value we're getting for Pn, we want to still be getting for Pn plus 1, right? We don't want to change the results. And that means when I plug in most of the data points into here, and I get the same result I had from here, that means this new polynomial Q should actually be giving me 0 on most of my data points. So let's write that here. For all our old data points, x0, x1 up to xn, this new polynomial should be giving me 0. It shouldn't be having any effect on interpolation of the old data points that we've already taken care of. Okay, so let's see if we can write down a polynomial that actually does that, that gives me 0 at all of those points. Right? Another way to say that is that this polynomial has roots at x0, x1 up to xn. Okay, so if we write our polynomial in a factored form, this is what we get here. Right? X minus x0 times x minus x1 all the way up to x minus xn. And if we go count the terms here, we've got a 1 term here, 2 terms here, all the way up to n plus 1 terms here. This is already an n plus first degree polynomial, so we can't add any more x's into the mix. The only freedom we would have is to multiply by some constant here that we'll call an plus 1. Okay, this is the general form of a polynomial that has the properties that we need. In other words, it vanishes on all our old data points. And now if we're going to throw one more new data point into the mix, the new data that we have should determine what this coefficient should be. This is what we expect our polynomials to look like. Okay, so we have our 0th order polynomial, which is obviously just a constant. Then our linear polynomial should involve something like x minus x0, right? All the old data points. And at this point, the old data point is only x0. Okay, our next term, our a2 term, would involve, again, all the previous data points, so x minus x0 times x minus x1. And we keep going. When we get to our nth order term, it should involve this product of all our previous data points, x minus x0, all the way down to x minus xn minus 1. Right? That's the form of polynomial we get if we're adding this type of Q on every time. Okay, so these are our basis functions, right? We've talked about different basis functions before. We had the monomial basis that led to these van der Waals systems that were not very nice. We had our Lagrangian basis that was kind of easy to work with, but potentially very expensive. And now this is our new basis. Our new basis involves these products. Okay, these products involve x minus, and then all of our old data points coming in here. Okay, and the data we have, the xi's and the yi's, will decide what these coefficients, what these a's should be equal to. Okay, so let's see if we can figure out some of these coefficients. To do that, we start plugging in data. So we start plugging in x naught first of all. Well, if I plug in x naught, right, this term is going to be 0. The next term is going to be 0. All these terms are 0. All that's left is my constant term, a naught. Okay, so plug in x naught, I get out a naught. That's what the polynomial gives me. Now what I want it to give me is y naught. We're trying to interpolate this data point. So right away I know what my a naught is. Now we do the same thing for x1. I plug in x1. Well, at this point I get my a naught. Here I get an a1, x1 minus x naught. Now we know the next term involves a product, and one of the terms in the product is x minus x1. Well, if I plug in x1 into there, I get 0. If I plug in x1 into here, I get 0. All the rest of these terms are 0. So what am I left with? I'm left with just my constant term plus my linear term. Everything else was 0. We already figured out what this constant term is. It's y naught. So I know that my polynomial gives me this expression here. And we know we're trying to do interpolation. When we plug in x1, we want to get y1 coming out. So now we just have to solve for a1. So we solve for a1 and we get this expression, y1 minus y naught over x1 minus x naught. Okay, let's just look at this for a minute. It feels a little bit like a first derivative, right? We've got rise over run. And we want to keep that in the back of our head. So when we did 0th data point, we got just the function value itself coming out, y naught. That's like a 0th order derivative. When we went to the next order, to x1, we got something that feels like a first derivative coming out. So we can maybe guess at that. Maybe we'll get something that looks like a second derivative when we go to the next term, and so on. And that will be important for trying to pull some structure out to figure out what these coefficients really look like. So let's go to the second order term. Okay, so we get, again, our constant term when we plug in x2. Our linear term, so here's a1, this is the a1 we just solved for, times x2 minus x naught. Go to our quadratic term. Okay, we had an x minus x naught times x minus x1, so we replace the x's with x2. Okay, and again, everything beyond that is going to give us 0. Now, again, we need to solve for a2. Okay, solving for a2 is easy. What we want to do is solve for a2 and write it in a way where we can kind of see some structure going on here. And our hypothesis was maybe it looks kind of like a second derivative. So I'm going to try to write this in a way where I can factor things a little bit. I have a kind of differences here. I have of y1 minus y naught. If I could get another y1 minus y naught here, or y naught minus y1, then I'd be able to factor things. And these kind of differences in y make sense. If we're trying to build up things that look like derivatives, we want differences. So let's just subtract a y1 from both sides. So here, y2 minus y1. Here, I'm going to have a y naught minus y1 times 1. Now I'm writing 1 this way. Why am I writing it this way? I'm writing it this way just to come up with a common denominator. So everything will be over x1 minus x naught. Okay, so here's this term, y naught minus y1. And then, again, I can factor a y naught minus y1 out of here. I get a sign flip. And what's left? X naught minus x2 over x1 minus x naught. So that's all of that. And then I have my a2 term. Okay, we simplify a little bit. Remember, I brought all this over a common denominator. That means I can add these numerators together. The x naughts go away. Just left with something pretty simple, x1 minus x2 over x1 minus x naught, and my quadratic term. All right, so let's solve for a2. If I solve for a2, I'm going to be dividing everything by x2 minus x naught, certainly. So that goes in the denominator. I'm going to be dividing everything by x2 minus x1. Well, here there's already a term that looks like that, so that will just go away with the sign flip. Okay, so you can see that here, there's the sign flip. And that remaining term, y1 minus y naught over x1 minus x naught. So I've moved to the other side of the equation. And again, this x2 minus x1 divides out this y2 minus y1. So that's this first term here. Okay, so do we see the structure here? Again, if I look at this term, this looks like a rise over a run. It looks like kind of a first derivative. This looks kind of a first derivative at different points. And now I can think of this globally as another rise over a run, right? So this is now the rise in the first derivative at a later point minus first derivative at an earlier point, divided by the run, x2 minus x naught. Okay, so it's not exactly a second derivative, but you kind of have the feel of a second derivative, this rise over run within a rise over run. And this is the kind of structure we want to try to pull out. Okay, and we could keep going. It gets messier, obviously, as we go along, and that's why we want to pull out this nice structure. But we could certainly solve for more coefficients. Again, it gets messier, so we need to simplify notation a little bit. So to simplify notation, I'm going to introduce these divided differences. So my 0th order divided difference, use the square brackets to denote the data points that are involved, is just going to be the corresponding yi, right, which is like my 0th order derivative. Okay, then a kth order divided difference is going to involve not just this data point, but the next k data points. And what I'm going to do is write this in terms of lower order divided differences. Okay, so just like on the last page here, if we can get back to the last page. There we go. Just like the last page, right, I had a difference of something that looked like a first order derivative, or in other words, a first divided difference, and another divided difference. Now I'm going to have a lower order divided difference. So this, right, this doesn't start at I here, it starts at I plus 1 up to I plus k. So this is really a k minus first order divided difference. And this, again, is another k minus first divided difference. They're just starting at different points. And then here I'm dividing by the run, the latest value of x minus the earliest value of x. Okay, and here is my claim. My claim is that these divided differences exactly give us the coefficients. We saw things like this before for A0, A1, A2, but my claim is you can do this in general. We build up these divided differences one at a time, and then we can extract the coefficients. In other words, our nth order polynomial would involve this 0th order divided difference, and then our first order divided difference times our linear term. Okay, a second divided difference times our quadratic term, all the way up to this nth order divided difference times an nth order term. Okay, you can prove this using mathematical induction. I'm not going to put the proof up here. I will post a proof to Canvas so you can read through that yourself and convince yourself this actually works, because what we've done here is maybe reasonable. We saw the structure for lower order terms, but it's not obvious, so we do need a proof of it. But let's just look at how we would compute this in practice. So again, we want to do this in a way where we don't necessarily know ahead of time how much data we should be using. So we'll have a list of these are the data points available to us, x0, x1, x2, x3, and so on. But we don't want to build up all the coefficients for them right away, not unless we really need them. Okay, and then here we're going to be computing these divided differences as we go along. So what's our first step? Our first step is to say we should bring in our 0th data point, the first one we have. And that lets us compute the 0th order divided difference, right, which was just y0. Okay, and that's easy to do. Now we say that's not good enough. We should really bring in more data. So if we bring in more data, what can we do? We can compute this first order divided difference now, and that's just y1. And then we go up this direction. And once we have these two things, we can take a difference of them, right? Divide by x1 minus x naught, and we get our first order divided difference. Okay, we decide that's not good enough. Well, let's add in another data point. Okay, so we add in another data point. That means we can compute our 0th order divided difference using this new data point. That was just y2. Once we have these two guys, we can compute a first order divided difference. And to get x2 in here, we need our quadratic term. We need a second order divided difference. So we can do that now. Once we have these two first order divided differences, we can use them to compute the second order divided difference. So again, we're going to be moving up the table in this direction as we compute things. Right, and you could keep going. If you decide, well, I really need another data point, we can add it in. So we can compute the 0th order term, and we say using these two adjacent 0th order terms, I get a first order term. Using these two first order terms, I can compute a second order term. And now using these two second order differences, I can compute my third order difference. And that's what I would need in order to get my coefficients. So again, we move up the table this direction. And what are our coefficients? Our coefficients are these things at the top of the table. So this is A0. This is going to be A1, A2, A3. So we need the other differences in order to compute these guys, but these are the only ones that will actually show up in our coefficients, in our polynomial. Okay, so if you're doing it by hand, this is certainly probably the easiest way to do it, is to do it in this tabular form. If you're probably not wanting to do it by hand in real life because you've got a lot of data to work with, you want a computer to do it, you need to write it as an algorithm. So I'm going to let you think about that a bit on your own time. How do we write this up as an algorithm? There's some information in your textbook that will help you to get you thinking like that and to be able to actually try to work this out yourself. And I just want to keep in mind, we get, okay, at the end of the day, an nth order interpolating polynomial. This is exactly the same polynomial that we got when we used the Lagrangian basis. The only difference is now we're using a different basis, right? So the theorems we had before about, okay, the interpolating polynomial exists, any other theorems we might prove about it are really the same, and we could use Lagrangian polynomials to prove things about them. This is just a different way of writing exactly the same polynomial. Okay, but there are some practical questions. All right, we want to know, well, in practice, what degree polynomial should I really be using? Right, and we said, well, maybe we decide 0th order is not good enough, so we go to first. We decide first order is not good enough, so we go to second, so on. But how would we really make that decision? How do we know when to stop? And in other words, this is the related question, maybe the same question from a different angle. How good is the approximation really? You know, can we estimate the error or put a bound on the error? If we know we're not allowed to have more than, say, 10 to the minus 3 error, can we figure out a way to guarantee that so that we're confident that the results we get are good? Because remember, we build this polynomial to fit some data, but then we want to use it to estimate our function f at other points, at points where we don't have data, and we want the estimate to be a good one. Okay, so let's try to think about how we could estimate error. Okay, again, this is important. Again, the polynomial we just came up with is the same one that we came up with when we did the Lagrangian basis. That means the theorems are the same, the error estimates are the same. So when we did our Lagrangian polynomials, we came up with an error estimate. That our error exactly looks like this. Right? It looks, so if we do an nth degree polynomial, our error is going to have the flavor of a next order term, similar to when we do Taylor remainder theorem. Okay, so similar to Taylor remainder theorem, right? We get an n plus first derivative evaluated somewhere, we're not sure where. We get an n plus 1 factorial. And now the difference is, right, we've got to feed in not x minus x naught to an n plus first power, but we have this product. Okay, so this is still an n plus first order term, right? We've got one term here, two terms here, up to n plus one terms, but now it's going to involve all the data that we use. Now, in a perfect world, more data means better approximation, right? That makes sense, that the more data we have about our function, the better kind of idea we have about the shape of this function, and the better we should be able to guess at its values in places we don't have data. So, in other words, what I'd like is if I have more and more and more data, n going to infinity, so an infinite amount of data, ideally, my approximation error is going to go to 0. That's what we want. Okay, so let's think about if or when this really holds. So I'm going to do an example, just to try to give us some concrete idea of what really happens with this error. So here's my example, 1 over x squared plus 1. Okay, this is a perfectly nice function, right? This is infinitely differentiable. Everything you would like to be true about a function is pretty much true about this one. So it should give us a good idea, at least, of what goes on when things are nice. So let's see if we can try to get an error bound for this function. All right, I've picked a domain, -5 to 5. And just to keep things simple, I'm going to assume that we have equally spaced data points, okay? So I have data point at -5, then, all right, here 10 is the width of my interval, so I'm going to divide the width of my interval into n equally spaced subintervals, right? So each time I add a new data point, I jump forward by a distance of 10 over n. So -5, -5 plus 10 over n, -5 plus 20 over n, and so on. These are all my data points, equally spaced. And I'm not going to try to get an error bound everywhere. Again, we're just going to start with a simple case and see what happens in a simple case, and then maybe we can try to generalize. So let's just pick a simple point to try to interpolate at. With data at these equally spaced points, let's try to estimate the function in between our 0th and first data point. So right in the center of them. Okay, so if the distance from here to here is 10 over n, then the distance from here to this point I want to interpolate is going to be half of that. It's going to be 5 over n. So the x I want to interpolate at is -5 plus 5 over n. We have an error bound. So this was our error bound, our 1 over n plus 1 factorial. I have no idea, we've got an n plus first derivative of our function. I have no idea where to evaluate it at, so I'm going to have to just use the worst case scenario on my entire interval. C just lives somewhere in this entire interval, that's all we know. Okay, and then the product of x minus all my different data points. Okay, and I take the absolute value. I'm trying to get a bound on the absolute value of my error. Okay, so just for a little bit of shorthand, we're going to call this our worst case error. We're going to call m sub n. All right, so if we use an nth degree polynomial interpolation, then we don't know exactly what our error is, right? We never know exactly what our error is, and that would be too good to be true. So all we can do is say this is the worst the error could ever be, and we give it this name, capital M. Okay, so we need to know the higher order derivatives of our function f. Okay, this was our function f over here, this nice function here. So we can start taking derivatives of it, and you can check using mathematical induction that actually this is a nice expression for the higher order derivatives. And we need to estimate how big this is. Okay, again, it would be hard maybe to get a concrete value for any possible values of x, so let's just try to get some bounds on these things. Think about what's an easy value of x to put in. An easy value of x is probably 0, right? This term obviously is simple when x equals 0. And most of these terms are going to vanish when x equals 0, everything except our constant term. So if we say do n even, and we're going from k equals 0 to n, then, okay, we have our x to the k term. That's our only non-zero term here. everything else, k is bigger than 0, and this is going to be 0. Okay, n plus k is 0, so this is a 1 here. This is a 1 here. So I plug in 0 into my nth derivative. I get n factorial divided by 1 times, and we decided all of this was 1. So the nth derivative is n factorial. Okay, that's pretty big, right? So we know that this function has infinitely many derivatives, but we didn't say how big the derivatives are. They exist, they're continuous, but they can get larger as n gets larger. And that's what we're actually seeing here. At least if we plug in x equals 0, the middle point, the derivative at this middle point is getting larger as we take higher and higher order derivatives. Okay, so what do we know about mn? We don't know exactly what it is. I haven't claimed that this is the, what do we need? We need the maximal n plus first order derivative here. I don't claim this is the maximal derivative, but I know that the maximal derivative is at least this big, right? It could be bigger. So when I look at my worst case error, well, this is going to be at least, it's an n plus first derivative, so at least n plus 1 factorial. So mn is going to be bigger than or equal to n plus 1 factorial over n plus 1 factorial. That cancels. And then we're just left with this product, the product of my different data points. So the worst case error is bigger than or equal to this product. So what do we need to do? We need to get a handle on how big this product is. Now that's not totally obvious, right? Some of the terms in this product are small. So if I go back to the picture here, right, I have x minus x naught. Well, if these are close points, this is very small. X minus x1 is going to be small. X minus x2 is still pretty small. But on the other hand, I also have terms like this, x minus xn, x minus xn minus 1. I go back to this picture, well, x minus xn, that's stretching across almost the entire interval. That's almost a width of 10. Okay, x minus xn minus 1, again, that's a huge distance, right? It's certainly bigger than 1. So we have the product of some things that are really small and some things that are bigger than 1. And when you multiply a bunch of small things by a bunch of things that are bigger than 1, how big is that? Well, that's not totally clear. So we need to do a little more work again to try to estimate this product. So let's see if we can get some estimates on it. All right, so I have x minus xi for all these data points. Those are the things that come up in this product, x minus xi, x minus x naught, x minus x1, and so on. Again, keep in mind, I know what x is. X has this form. I know what xi is. Okay, so I can work out what x minus xi is. It's 5 over n minus 10i over n. Okay, so here I've got that, 5 over n minus 10i over n. And I'm going to plug this in place of the products. So we'll do it for I equals 0, for I equals 1, and so on. So the product I want is this product. There's n plus 1 terms in the product because we started at 0. So each of these terms involves a 5 over n. There's n plus 1 of them. I can pull that outside the product. It doesn't depend on I. And then I have something that looks like 2i minus 1. Okay, just keeping in mind, when I equals 0, here I get a 1. So a 1 times a bunch of stuff doesn't change it. So I'm going to start at I equals 1 here. And now I flip the sign because I'm trying to make it all positive. So I get 2i minus 1. This is going to be 1 when I equals 1. It's going to be 3 when I equals 2, and so on. And we try to work out what this product is. Okay, this is a bunch of odd numbers multiplied together, right? With adjacent odd numbers, with the biggest one being 2n minus 1. So 2n minus 1, 2n minus 3, 2n minus 5, all the way down to 1. Now, what I'm going to do is also include the even numbers in there. So I had my 2n minus 1, my 2n minus 3, and so on. I'm going to also multiply both the numerator and the denominator by the even numbers, 2n, 2n minus 2, 2n minus 4, and so on. Okay, so what happens? In the numerator, well, now I have the product of all the integers up to 2n. That's 2n factorial. In the denominator, I have the product just of the even numbers. Okay, so I had 2, 4, 6, 8, all the way up to 2n. They're all even numbers, so I could factor a 2 out of every one of them. So I'd have 2 times 1, times 2 times 2, 2 times 3, and so on. So I factor all the 2's out. Here are all the 2's that I factored out. And then what was left was 1 times 2 times 3, and so on, up to n. I got an n factorial. All right, let's see if we can simplify this. Okay, so we simplify this. I'm going to rearrange things a little bit. So I'm going to have a whole bunch of n sitting here. I have n plus 1 of them. I'm going to move n of them into my denominators here. So these n, 1, 2, up to n of them. The last one stays out here. I'll pull a 5 out. I have 2 to the n here. I have 5 to the n left here, so that goes in this fraction. Okay, so what do I still have in the denominator? In the denominator, I still have an n factorial. That goes here. In the numerator, I have a 2n factorial of 2n times 2n minus 1, 2n minus 2, etc., times n factorial. Okay, so just keep in mind, I had 1, 2, up to n terms here in the denominator. And if you count these, this is n plus 1, n plus 2, all the way up to n plus n. So n terms here. So I can pair them like this. 2n over n, 2n minus 1 over n, all the way down to n plus 1 over n. N factorial over n factorial. So this simplifies a little bit. I have my leading terms. 2n over n is certainly bigger than 1. 2n minus 1 over n is certainly bigger than 1. All the way down to n plus 1 over n is certainly bigger than 1. This guy here is clearly equal to 1. So this product, I don't know exactly what this product is. I haven't worked out exactly what it is, but we know it's bigger than, okay, all of this here is bigger than 1. So the product is bigger than 5 over n times 5 halves to the nth power. Okay, again, that's not exact, but it's a much simpler expression to try to work with. So let's put that into my error bound. We said our worst case error bound was at least this big, maybe bigger. Our worst case error bound was at least this big. That means our worst case error bound is at least this big. So our worst case error bound is bigger than this. And then we think about what happens to this as n goes to infinity. Okay, we can take that limit. If we take the limit, we find actually as n goes to infinity, this goes to infinity too. So what was happening? Even though our error bound, here it was, right, has an n plus 1 factorial in the denominator, which obviously this goes to 0 as n gets big. We unfortunately have some things that don't get small. So we had this derivative that gets large. Right? They exist, they're continuous, but they get arbitrarily big, and that becomes a problem. And then we have this product that, it's not like the product we get in a Taylor remainder theorem, where we have something small to the n plus first power. Instead, we have to look at the product of all these different data points, and some of those get very small, but some of them don't. Some of them stay big. The overall product didn't get small on us. So our worst case error bound is not very good. It can get, in fact, arbitrarily bad. That doesn't mean things are guaranteed to go bad, but it also doesn't mean things are guaranteed to be good. Things could be fine, or they could be very, very bad. And this problem is called Runge's phenomenon, which is caused by overfitting. In other words, as we add more data, and we try to fit a polynomial to this data, we have to oscillate wildly to keep coming back to hit the data points. So I have a picture here. The blue curve is the function we were working with, right? A nice smooth function, but the higher order derivatives get very large here. Okay, so if we fit a quadratic polynomial to it, so n equals 2. Well, okay, this is certainly the best we're going to be able to do with n equals 2. Nice, a nice quadratic that fits this data at these, okay, n equals 0, n equals 1, n equals 2 points. But now as we add more data, we want to fit it here at 0, 1, 2, 3, 4. Well, what does it do? It's a fourth order polynomial here, so it hits the first data point, and then it comes back and hits the second one, and now the third, the fourth, the fifth. Now as we add more and more, what happens? It hits the first data point, and then it's got to try to swing back quickly to hit the next one, swing back to hit the next one, and so on. As we go up to n equals 12, well, it's got to try to swing back in a hurry, and we actually get these wild oscillations coming in, right? So this is n equals 12, and bigger, we are hoping for better results, but what we're actually getting is now these huge oscillations. This is Runge's phenomenon, and again, this is a result of overfitting. We add in lots of data. We say we want you as a polynomial to hit all these data points, and it's actually asking too much of the polynomial. In order to do it, it's got to bring in these wild oscillations, right? So this is not so good. This high degree polynomial interpolation is really not doing what we would like it to be doing. So let's think about this. Is this a problem for us? Certainly it's a problem if we want to do good interpolation. This is not good interpolation by any means, but just even theoretically, we proved a theorem a couple classes ago, this Weierstrass approximation theorem, that said, well, as long as I'm allowed to use an arbitrarily high order polynomial, right? As n is big enough, I can construct a polynomial of degree n, Pn, that gets arbitrarily close to my function f. Well, here, as I'm using higher order polynomials, I'm actually getting farther away from my function f. So how does that work? Can both of these statements be true at the same time? And the answer is there's actually no issue. So remember, our approximation theorem said we're guaranteed to have a polynomial that's close to f, right? As long as we use a high enough degree polynomial. But it never says that we were actually doing interpolation. It says we were doing function approximation. Not quite the same thing. So interpolation said nothing about really being close to f in between. It said I require you to hit the data at these points. Now, if I was using my Bernstein polynomials that we built, now the Bernstein polynomial may not hit this data point, right? It will get close to this data point if n is large, but it's not required to hit it. And that extra freedom that it's not required to actually hit my data at certain points, it just has to be close, is what allows it to smooth itself out and actually come close to this function. So we want to keep in mind this difference. It's not that more data is somehow giving us less information about the function. It's just we're requiring our interpolation here maybe to do a little bit too much. So it's still possible to do function approximation to get polynomials that come very close to our function. But interpolation is not the way to do it. If we want to come close to the function using polynomials, there's other ways of doing simple function approximation, and we'll talk about it. But if we want to use just a higher order polynomial to approximate the function and do it well, we can't require it to hit our data points like this. Interpolation is not the way to go. So what should we do? What if we really do want to do interpolation? And we want to do it well, right? We don't want these wild swings, these wild oscillations. We want something reasonable, that as we add more data points, we get better and better results. How can we do that? Well, what was the sticking point in our analysis? We had error formulas, right, that we could use to estimate the error, and they involved higher order derivatives. And these higher order derivatives had the potential to get very, very large. Well, it would be better maybe to work with error formulas that don't involve higher order derivatives. Right? Higher order derivatives were things that get big. If we could have error formulas that just involve lower order derivatives, these would be capped. If we said we're not going bigger than, say, a third derivative in our error formula, Well, this has a uniform bound. We can multiply that by something that gets smaller and smaller. Dividing that by something like an n plus 1 factorial, that really will go to 0. We want lower order derivatives in our error formulas, which suggests we need to work with low order polynomials. Right? The higher order polynomial we used, the bigger the oscillations we brought in, and this was caused by these higher derivatives that were getting very large. So we need lower order polynomials. Now, if all I do is say, let's fit a very low order polynomial, say a quadratic, to this whole thing, again, that's not doing good interpolation. This red curve, my quadratic, is not close to the blue curve that I actually want to approximate. So just fitting a low order polynomial isn't good, and just fitting a higher order polynomial isn't good. What we want to do instead, what we're going to try to do going forward, is to not use a single low order polynomial, but to patch together lots of different low order polynomials to get improved accuracy. And the idea will be, if I look at this function globally, it really doesn't look like a quadratic. But maybe if I just zoom in on a little piece here, right, just in this little window, maybe I could fit a quadratic to it and do a really good job. And then maybe I could move over to here, and just in this little window, I fit a different quadratic to it that will do a pretty good job. And so on. I move over to this window and zoom in on here. That's not too different from a quadratic. I could do a pretty good job. So that's what we want to do going forward. That will be called spline interpolation, where we're going to take some low order polynomials and try to patch these together. So we use each low order polynomial in a little window, try to patch them together in a way that we can get improved accuracy. So that's what we're going to do on the next class. For now, I'm going to leave this here.